Today we will have Ellie Pavlick from Brown University to give a talk at the Machine Learning at Georgia Tech seminar. Ellie was my former groupmate at University of Pennsylvania. So she is very have many interesting research interests. He's always like running in front of others. Did very early work on understanding contextual word embeddings. So that's look like what she will be going to talk about primarily today. But on the other side, she actually started doing some robotics and NLP interdisciplinary research recently. She also work quite extensively in human in the loop kind of crowdsourcing related research. Has a very broad interest. She's also leading multiple big projects, including when we are working together for IARPA, multilingual information extraction in information retrieval. So that has been going on for more than a year. So I got to see Ellie like almost every week. It has been fun. So yeah, without further ado, I will let Ellie talk about her own work.
Thank you so much, Wei. Thanks for the introduction. And yeah, it's been fun. I've known Wei for so long. It's a shame to not get to go visit there in person. But I really appreciate the invitation, and it's been fun seeing you so much recently. And yeah, thank you all for attending and for hosting me, I guess, virtually. So today I was going to talk about some work that kind of spans the past couple years. As Wei mentioned, I've been recently very interested in kind of contextualized word embeddings, so language models, basically what they do and don't represent about language. And so this is kind of a somewhat linear story of some of the work we've been doing since around 2018, kind of building on these questions of trying to understand like kind of why they succeed and why they fail in the ways that they do. So just acknowledgement to all of my collaborators, in particular, Ian Tenney, who I've worked with a lot at Google, who is a driving author on a lot of this work, and my students, Charlie Lovering and Rohan Jha, who are students at Brown and are, again, lead authors on a lot of the work I'm covering, and then several other collaborators. So over the past 2 to 3 years, there's been a lot of work on trying to understand what do these deep language models understand about language. And I'd like to kind of organize the work that's been done into 2 broad categories. So kind of one kind of approach has been really focused on asking what types of features the representations encode about language. So this uses a technique called probing classifiers. And then the kind of parallel line of work that's very related but slightly different asks, do models behave like they're using specific types of features? And I think of this technique as called challenge tasks. So just to kind of set the stage for the work I'll be talking about later, I want to give an overview of what's been happening in these in both of these kind of sides of this analysis over the past couple of years. So on the first question, so this is really people asking, is some specific type of feature encoded by our language representations? And here we're dealing with these neural language models. So if you're not familiar, if you're not an NLP person, they're basically just big neural nets that are trained on some version of predict the missing words or predict the next words. So you would say you get an input sentence, and you're training the model to say, okay, you're about to start a sentence. What do you think the first word should be? And it predicts something like the, and you say, good job. Okay, you predicted the word the. What do you think the next word should be? Predict something like car. And they're just trained in this way. So it's kind of a self-supervised training method that results in, it turns out, very good representations of the words themselves. So very often we don't care about this task per se, although often we care about generating language, but more often we care about the representations we get of the individual words. So the vector for the vector for car, the vector for is not in blue. And so then the question is, what do these vector representations encode that earlier representations of language that we had didn't necessarily encode so well? And so the technique we use a lot in this kind of study is, like I mentioned, they're called probing classifiers or diagnostic classifiers. And the idea is we take these representations, which have been trained to do this task, and we freeze the network so you can't make updates to the vectors themselves. And then you put some classifier on top of those representations and you ask, for example, does the vector for car contain the information that car is a noun? Or does the pair of vectors for car and blue together, can I recover the fact that blue was a modifier of car in this sentence? And so this is some work from iClear in 2019 with Ian Tenney and a couple other collaborators, where we were looking at basically for lots of different types of linguistic features we care about, how well do these representations encode those features? And specifically, we're looking at all of the different features that kind of come from the traditional NLP pipeline. So this includes, for example, part of speech tagging. So we would like to know that Disney is a noun, is a verb, brand is a noun. And then usually kind of in pre-neural times, right, we would train a model to explicitly produce parts of speech, and then that would get fed into some later layer that might do something like entity recognition. So we would care about the fact that Disney refers to kind of an entity in the world, something with a Wikipedia page, for example, whereas the word brand is a common noun that does not have that kind of entity status. We do things like parsing, so you would want to know that it is the subject of the verb is and global brand is the object of the verb is. And we might do things like co-reference, so you would want to know that that Disney and it are referring to the same entity in this sentence, right? And so these are kind of increasingly these are increasingly maybe abstract levels of linguistic annotation or kind of linguistic processing that build on each other and serve as the basis for a lot of the NLP models that we would build kind of back in the day, right, where you would do each of these tasks explicitly. And so the question is whether these language models trained in the self-supervised way I just described capture this kind of information kind of for free. And so we can look at all of these different tasks that go kind of follow along the pipeline, and we can look at how well a model does in accuracy on these tasks if we just start with the word prior. And you can see this is the kind of annoying thing about NLP or language data in general, is that the word priors are very good. So like if I have a word like car, I have a pretty good guess that it's going to be a noun, and I don't need to know much about the context in which it occurs. Similarly, if I see a pair of words, one of which is blue, I have a pretty good guess that the dependency relation there is going to be a modifier relation, because blue often when it occurs as a modifier, right? You can see that the word priors are quite high. But even so, when we train these models, we get very significant gains, in many cases close to comparable with state-of-the-art models trained to do these tests directly. So you can see that it's a little easier to look at if you look at the delta over the word prior, and you can see that in many cases double-digit gains in terms of how well the contextualized models are encoding this kind of information. We can go a little bit deeper, and in a follow-up paper we looked at not just like whether the information was there, but kind of how it was organized. So I'm going to show a fairly complicated figure, so bear with me, I'll work through it. But these models are extremely deep, so these language models are often many, many layers. In this case, we're looking at the BERT model, which is a 24-layer model, the BERT large model. So what you're looking at here is a figure that's going from left to right. Each bar is, or each kind of column in this figure is looking at one of the layers of the network. And the important thing is that the later layers can depend on the earlier ones. So if we're trying to learn increasingly abstract representation, similar to how in computer vision, you kind of start with things like, basic edge detectors, and then maybe you get shape detectors, and you can move up to like cat detectors. We would imagine something comparable here in language, where you would start with kind of lower level linguistic information and build up towards higher level information. And these blue bars are regression weights. They're our way of measuring how important a given layer is to making a decision about one of these linguistic features. And so you can see across these different tasks we're looking at, part of speech, constituency parsing, dependency parsing, et cetera, that the kind of organization follows the pipeline structure that we're expecting. So this kind of part of speech information, which is kind of considered lower level, happens a bit earlier in the network, whereas things like co-reference resolution, which depend on having good part of speech and good parsing, that happens much later in the network. So while we can't really say that there's a real causal relationship going on here yet, there is definitely, the signal is consistent with the model doing the right thing, right? Like learning these low-level linguistic features, using them to form more abstract linguistic features, and then eventually arriving at representations that are competitive with explicit models trained to do these tasks. Great, so that was some of our work on this topic, but I just want to highlight that we are far from the only people working on this question or applying kind of probing classifiers to this task. So another highly visible result in this area was work by Hewitt and Manning in that same year in 2019. And they were looking at these same contextualized language models and basically trained a model to project from the embedding space to something like an explicit syntactic parse tree, and showed that you could do that with state-of-the-art accuracy. There was also great work at iClear the same year, looking at kind of at the neuron level within the network for evidence that you could differentiate linguistic concepts like verb tense or grammatical gender, and they showed that that was also recoverable with very high accuracy. And there's been a battery of other types of results. So my kind of summary for this left-hand side is that there's been kind of over the past couple of years this mounting evidence of people suggesting that these models really do contain a lot of linguistic information about the sentences. So they don't just contain what we often refer to as a bag of words type of representation, but rather they do seem sensitive to quite a bit of non-trivial linguistic structure. Okay, so that's on that kind of first side. But like I said, there's been a lot of work happening in parallel. So at the same time, people have been looking at whether models behave as though they have access to these rich types of features. And so there the question is whether some type of feature, be it part of speech, dependency parsing, et cetera, is actually used by models to make decisions. So we can think about some of the kinds of tasks where these things are important. You can imagine something like a basic inference task. So here what we want a model to do is take as input a pair of sentences, like there are apples and bananas on the table, there are apples on the table. We would refer to this as the premise and the second as the hypothesis. And the task is to predict whether the premise entails the hypothesis. So whether the hypothesis like logically follows given the premise. And in this case, obviously the answer would be yes. If I were to make a small change like apples or bananas, then the hypothesis doesn't necessarily follow. So this is in a study with Tom McCoy and Tal Linzen, who are the lead authors on this from Johns Hopkins. So here we were looking at whether models were using kind of this rich syntactic knowledge that they appear to have access to in order to reason about these kinds of inference tasks. So we designed sentence pairs that look like this, where basically all of the words in the hypothesis appear in the premise. But sometimes this hypothesis is entailed and sometimes it's not. So you can see in the first case, the hypothesis is entailed, in the second case, it's not. And the reason for designing it this way is kind of the hypothesis was that if the models are using kind of rich syntactic structure, then they should be able to differentiate between these two cases. For example, by reasoning about dependency structure or semantic roles, which we saw earlier, they capture fairly well. But if they're not actually using those features, they might fall back on some kind of dumb heuristic, something like lexical overlap, and then they'll actually predict entailment in both of these cases, despite the fact that there is obviously a structural difference that would allow you to separate the greens from the reds. So we evaluated a set of models that were at the time state of the art, and this includes the BERT model I was describing before. And on a kind of standard test set, the MNLI test set, they all perform competitively. If you test them on examples like the green ones, so where all of the words in the hypothesis appear in the premise and the sentence is entailed, they get near 100% accuracy because they always predict entailment. But if you test them on examples like the red ones, they get close to zero accuracy because they also always predict entailment. And so this type of result has been, again, kind of was surprising at the time and has now become almost like a platitude, right? Like that, how readily these models appear to be making decisions for the wrong reasons or using dumb heuristics. So there's this example of them using lexical overlap. Another pretty high profile one has, this is work from Rachel Rudinger, but there's been a lot of similar work on looking at kind of like co-reference and how models will exploit kind of biases like gender, profession, co-occurrence, rather than reasoning about the syntax of the sentence. There's some of the early work in this area, which I really liked, was came out of Stanford. They basically took a question answering model and just added random distractor sentences into the document from which the answer was supposed to be derived, and this caused models to lose about half of their accuracy, despite the fact that these sentences were really unrelated to the question the model was trying to answer. So overwhelmingly, the results kind of using this challenge task type of approach has suggested that models really aren't solving tasks by using these rich features, right? So I think this kind of setup has been really fascinating to me. I'm just thinking through how kind of these sets of results coexist and why we're seeing exactly the patterns we're seeing. So on the one hand, it seems that you can extract this linguistic information from models. They do appear to have access to it, but they don't seem to use it to solve tasks, even when they really should be using it to solve tasks. Like using these features would allow them to do the tasks better. So what's going on? So I'm going to just talk through 3 kind of sets of results from some recent work that kind of test different hypotheses about what might account for this disconnect that we're seeing. So the first kind of thing that came to mind, and when I was brainstorming and talking to some of these other authors that we've been working on this, is maybe there's nothing weird going on at all. It could just be that the features that come as a result of pre-training get erased during fine-tuning, right? So that we have some kind of catastrophic forgetting going on. So even though the pre-trained language model had access to dependencies and semantic roles, when we fine-tune it to do something like the inference task, it just quickly overwrites all of those features and it no longer has access to it. So we tried to look a little bit more closely into whether something like this is happening. And this is results from Amal Merchant, who is an AI resident at Google. And we were looking at quite a lot of things in this paper, but I'm just highlighting a few of the results, and particularly whether these linguistic features that we said were present as a result of the pre-training procedure are still there after fine-tuning. So this is the same kind of figure I showed earlier, where I was saying that the BERT model contains a lot of signal that is not available in the lexical prior. And what we did is we just fine-tuned that BERT-based model on a large number of tasks, so trained it to do inference or question answering or something like that. Not a large number, a small number actually. And see if the performance on this any of these probing types of tasks drops. And what we see is not really. So there's some fluctuation, but it's hard to say whether any of this is outside of random noise. The one exception being if we fine-tune on the dependency parsing task specifically, you can see it improves constituency parsing. That's something we've talked about and might follow up on, but for the most part, we don't see anything that suggests that the information is really lost, especially not to the extent that the model could no longer use those features for a downstream task if it was needed. We can look at this a little bit differently. So these are using those kinds of probing classifiers I mentioned before. I also mentioned that Hewitt and Manning paper that tried to train a projection from the contextual embedding space into parse tree space. So these are results using that type of analysis. I won't get into the weeds on the metrics because it's kind of parsing specific. So if you're not an NLP person, it might not be, it's not that interesting. But what we really care about here is the difference between the blue line and the other lines, right? And so here you can see that when we fine tune on a task that's explicitly a syntactic task, so dependency parsing, we do improve the quality of the encoding of these linguistic features. So it does get better in some cases. But when we fine tune on the question answering or the inference tasks, we don't really see that it gets worse relative to the baseline model. in any significant way. So our kind of takeaway there was that we can't really explain this problem we're seeing by a catastrophic forgetting issue, because we don't really see these significant drops in the probing accuracy following training on the new tasks or following fine-tuning. Something else has to be going on that would explain why the features are not getting used to solve these tasks. So the kind of second hypothesis, and I think maybe the most intuitive one, is that maybe there just isn't enough signal in the training data to begin with. And so the model just doesn't know that these are actually features that it should be using. Like it doesn't know that dependency parsing is important for natural language inference. And like I said, I think this is a very intuitive and it's a good hypothesis as a starting point. So I showed this result for this lexical overlap study, where we see that these models are using this lexical overlap heuristic rather than reasoning about something richer. I left out the detail that the training data the model had access to looked something like this. So actually only about 1% of the examples in the model's training data contained lexical overlap, and of that 1%, only 10%, so 1/10 of 1%, was the label non-entailment. So actually, we're asking the model, in order for the model to perform well on these red bars, we're asking it to extrapolate based on 1/10 of 1% of its training data. And if we just add additional examples to the training data, so we blow it up so that now actually 10% of the training data has lexical overlap, and there's a 50-50 split between the labels associated with the lexical overlap, then the models perform quite well in both cases. And so this is a method called data augmentation, which has been increasingly studied in NLP, especially for issues related to like bias and fairness. I mean, generally improving models' robustness to quote out of distribution test examples. So we wanted to look more closely at whether this really makes sense as a solution for improving models in general, or for getting models to be more robust in general. Like, is it the case that if data augmentation is a good solution, then it should be the case that we can really just, we could add additional training data and expect models to generalize as expected or as we want them to across the board, right? So we came up with a kind of synthetic setup to test this in a way that we could reason about a bit more carefully. So our general setup is we have some machine learning problem, we have things labeled as positives and as negatives, and there's some target feature in this space that perfectly predicts the label. So anything that's in the blue circle, the label is positive. And there's some spurious feature that is unrelated to the label but overlaps with it. So anything red may or may not be positive, or it could be negative. The problem, which is I think representative of most machine learning problems these days, is our training data is skewed in some way. So we've sampled some training set where the spurious feature actually has very high overlap with the target feature. And so as a result, a model that is trained on this data could very reasonably think that the spurious feature is actually the thing that predicts the target or predicts the label and get high accuracy even if it ignores the target feature. But at test time, what we want to do is train on the full space, or particularly we're interested in testing on the cases that decorrelate the target and the spurious feature. So we would want the model to still predict well in the case where the target occurs without the spurious, or where the spurious occurs without the target. That's kind of our goal, is a robust model should perform well on those sets despite having trained on this biased training set. So the question is really whether the rate of co-occurrence, the assumption with the data augmentation approach is that the rate of co-occurrence of the target and the spurious feature during training, that alone will explain the test performance. Because when we do data augmentation, what we're going to do is basically deliberately manipulate this rate of co-occurrence by adding new examples that either, include the spurious without the target or the target without the spurious. And the assumption is that by doing that, we will improve the model's generalization to these test samples. So that's what we're interested in testing right here. So again, I said like I said before, we set this up as kind of a toy simulated task so that we have a lot of control over how things work. So we give our sentences, our sequences of numbers, and we're training it like a sentence acceptability task. So basically, the sentence is in the language if it contains the target feature, regardless of the spurious feature. So we try a few different types of target features. So, for example, in one case, the target feature is just whether the symbol 1 occurs anywhere in the sentence. In another case, the target feature is whether the first two symbols in the sequence match. Another one is whether there appears some duplicate or some pair somewhere in the sentence, but it can occur anywhere in the sentence. And the last one is whether the first and the last symbol match. And then in all cases, our spurious feature is just whether the symbol 2 appears anywhere in the sentence. So we can look at how models perform in this case. And we start by looking at how they perform in the setting where the training distribution is the spurious and target are perfectly correlated. So there's no basis for the model to be able to know whether the spurious or the target feature is predictive of the label, right? The training data has given it no incentive to prefer one over the other. And we can look at the error rate in the two cases I talked about before. So error rate when the spurious feature occurs alone, or error rate when the target feature occurs alone. And what's interesting to see here is that in this first case, when we have this contains 1 as our target feature, we're actually not getting 100% error, despite the fact that there's no real incentive. So we're seeing that the model is kind of making a lot of random guesses in this case, whereas in all of the other cases, we actually are getting 100% error. It has chosen to use the target or the spurious feature to make predictions rather than the target feature. When we increase the training data, we augment the training data just super slightly. So we just make it so that 0.1% of the training examples contain the spurious feature without the target feature. So it basically decouples these two features. Then actually in the contains 1 case, the model solves the task perfectly. And this is an interesting setting to point out because this 0.1% is actually what we had in that NLI, that natural language inference setting I showed earlier. So this is a teeny sliver of the training data, but it is enough for the model to extrapolate and learn the right thing in the case of the contains 1 feature. In all the other cases, it actually still completely fails. If we augment up to 10%, then we start seeing movement in some of the other features, although they're definitely not solved. As we move up to 50%, in some of the cases, the model seems to perform well and nearly solve the task. In this last case with the last target feature, it's still getting very high error when the target feature occurs alone. So summary of these results. I think the picture here gets a little more complicated, right? So when we think about something like data augmentation, it seems to be that we can't really just blame this on the training data. If it was really a problem with the training data, then data augmentation should work similarly across all settings. But we actually see that different features respond differently to the same intervention in terms of data augmentation, which suggests there's more going on in the problem than just learning feature co-occurrence during training, right? There's some additional dimension to that affects whether or not the model will make decisions based on the spurious feature versus based on the target feature. So that brings to kind of a last hypothesis here, which is that maybe there's more going on, so it's not really a matter of whether the feature is, quote, there or not, but we need some softer notion about how available the feature is to the model when it begins training. And so kind of stepping back and thinking about what we're dealing with these kind of neural language models, I think it's nice to draw the parallel to what we kind of think about classical machine learning before everything was end-to-end. So in a kind of classical machine learning setting, we think about two pieces of the model, right? There's features and then there's weights. So you would spend time doing feature engineering, extracting good features that you think are relevant to the task you care about, and then the machine learning part would learn a weight vector that would decide how much to care about those different features that you provided it. the thing that happens in this end-to-end setting, like what we have in these neural language models or any of these neural nets, is that they are simultaneously updating weights, but also updating features. So when the model is trying to learn how to do something like language inference, and it's coming in with some representation of language to start with, there's a bit of a decision that it has to make. Sorry for anthropomorphizing models, I can't help it. I'm not implying that they're conscious or anything, I anthropomorphize everything. So yeah, that has to decide between learning better features, learning a better way of representing that language, or just learning better weights over the features it already has. And actually it can do kind of both of these things in parallel, but they kind of are conceptually different parts of what type of learning is going on. And so you can imagine that if the model gets as input some feature representation that's just a very bad match for the task it's trying to do, it might be better to spend a lot of time learning new features and actually so that it can learn simpler weights over those features. Whereas if it gets representations that are already nicely aligned with the task it wants to do, it can just focus on learning a good set of weights. And these might be like different levels of hard, different amounts of work for the model to learn better features versus learn better weights. So to kind of formalize this notion between how hard the features are to extract from the input representation, visually it obviously makes sense if you kind of think about how separable are the different classes or the different features we're interested in. There was a really nice paper at NACL or ACL, I forget, last year by Elena Vojta, and here they defined a nice notion of minimum description length for thinking about this difference. So minimum description length has been around for a while. It's an information-theoretic notion, but the kind of intuition is that the MDL is supposed to describe how efficiently you could communicate the labels given the data. So it's some kind of code length. Again, it's coming from information theory, where a shorter code length means that you can more efficiently transmit those labels. So the labels were better encoded given the data. So that there's a kind of formal definition of it. I have another slide. The important thing to know is that the harder the features are to extract, the higher the MDL, the easier to extract, the lower the MDL. In terms of how this is actually computed, it's in practice, and there's a proof of this in the Vojta paper. It's basically the area under the loss curve as a model is trying to learn to separate, in this case, blue from red from purple. So you can think about that if it makes more sense. So kind of the harder it is to learn that, the lower that loss curve is going to decay and the higher the area under the curve. And so this kind of notion, if we go back to a picture like this, so we can see here that features responded very differently to this data augmentation, right? So the contains one feature basically just caved instantly as soon as we gave it 0.1% of training data examples to nudge it in one direction, instantly solves the task. And if we look at that and we compute something like the MDLs of the spurious and target features, they're measured in bits. So the metrics themselves don't matter, more just the relative one. But you can see they're both low and about the same for both the spurious and the target feature. Whereas if we look at something like this last one, which was very stubborn and the model really struggled to learn it even with a really nice training distribution, here we can see there's a huge difference between how easy the spurious feature is to extract given the input data and how easy the target feature is. Specifically, the spurious feature is much easier to extract than the target feature. So our hypothesis in this work, and this is actually my year on the slide is wrong, this is iClear coming up this year. So we wanted to test this hypothesis that that fine-tuned models, whether they use the target feature, is a function of how hard that feature is to extract relative to whatever competing spurious features also exist in the training data and the data distribution. So the co-occurrence between the target and spurious feature during training. And we refer to this as the evidence. Basically, the lower the co-occurrences, between those two features, the more evidence the model has to choose one over the other. If they co-occur perfectly, the model has no evidence to base its decisions on, so it's going to be at chance between choosing between these two, or actually, in fact, not at chance, but then dependent on the extractability of the two features. So yeah, again, so the training evidence, we're using that phrase to refer to the co-occurrence between the two features, basically the size of this purple region. And when we talk about use of the spurious feature, again, we're not making a causal argument just yet. That's, next work. So we're just going to talk about the performance on these held out test sets that decouple the spurious and target feature. So we'll report F1 score over these types of test sets, and we refer to that as whether the target feature is being used. If the target feature is being used, then the F score should be high. And then finally, when we talk about the difficulty of extracting the features, this is really a relative measure. So it's the MDL of the spurious feature over divided by the target feature. So the higher this is, the lower this is, the easier the spurious feature is to extract relative to the target. When it's higher, it means that I always get this wrong. I need to. So when the spurious MDL is low and the target is high, then this ratio will be low, meaning the spurious is easier to extract. Right? And then as it gets higher, it means the target becomes easier to extract. Great. So our experimental setup. So here we want to switch out of the toy setting, and so that we can test kind of real language models like BERT and the models I was talking about at the beginning of this talk. So we are going to design a sentence acceptability task that's using English sentences, but we're going to kind of design simple templated sentences so that we have control over the spurious and target features. And so the sentence acceptability task is just, it just asks the model to predict yes or no, is this a good grammatical English sentence? So in this case, the piano teachers see the handyman, that's a fine sentence, so the label is yes. If you were to change this to something like the piano teachers sees the handyman, that's no longer grammatical, all right? So the answer would be no. And the target feature in this case that we'd want the model to use is something like subject-verb agreement. So the fact that teachers is the subject of C, and so therefore C should agree with, in number with teachers and not with lawyer or any of the other nouns in the sentence. That would be the target feature that we would like the models to use to make these decisions about acceptability. But then we manipulate the data so that there's many other spurious features that occur during training that the model might use instead. So in one setting, for example, we just append random words like often to all of the grammatical sentences so that a model could just assume that maybe the task I should do is just basically if the sentence contains the word often, then it's grammatical, otherwise it's not, which is not the feature we want it to use. It wouldn't generalize outside of training, but based on the training data, it might be a strong signal. We also played with some other spurious features, so like sentence length, maybe grammatical sentences are longer given the training data. Maybe grammatical sentences just happen to contain more plural nouns. Maybe grammatical sentences have this feature where the verb tends to agree with the closest noun, not with its subject, things like that. So we come up with 20 target spurious feature pairs. They're all listed here. The details of them are not important. The important thing is that they capture a range of values of this ratio that we're interested in, this relative extractability. So for example, here's 3 of them, the subject verb ones. We also look at things like negative polarity, item licensing, and filler gap dependencies. These are 2 other syntactic semantic phenomena that affect acceptability. And so you can see these range from having very low ratios, which means that the spurious feature is much, much easier to extract than the target, to having very high ratios, which means the target feature is actually much easier to extract than the spurious, given the input representation. And so for the results, we're going to compute, like I said, the average F score over these kind of held out test sets. So in this case, we train on the training set with some level of co-occurrence, usually a high co-occurrence, but we manipulate it during training. And then at test time, we're going to look at the average over these test sets that are drawn from these deliberate regions of the space where the features are decoupled. And you can see a very strong correlation here between the relative extractability of the features and how well the model performs on average. And this is averaging across a lot of different training ratios. So basically you can see each point here is referring to a feature pair. And we're training the model using a lot of different linguistic representations as starting points. And for like BERT, Roberta, T5, you can see, and GPT-2, actually, you can see all of them really track this clear trend where the easier the target is to extract relative to the spurious, the better the performance overall. And we see that bad performance happens when the spurious is much easier to extract than the target. That's when it learns a solution that doesn't generalize. We see a similar trend with GLOVE, but it doesn't perform as well. GLOVE is not a contextualized word embedding model, but a static word embedding model. It just means it's less powerful and it actually doesn't solve the tasks in many cases. So I could talk more about that if anyone's interested. You get an even more complete view if you kind of break this down by looking at that the use of the spurious feature on the y-axis as a function of the co-occurrence between the target and spurious during training, and you look at this at different levels of that extractability ratio. So for example, here we can look at this red bar. This is a case where the target is actually very easy to extract relative to the spurious feature. And we want to see the y-axis is error rate, so we want to see low values. And in this case, we actually see the model performs perfectly, even when it's given training data that provides it absolutely no evidence to do the right thing, right? So here we have, pathologically designed training data where there's a spurious feature that perfectly predicts the label, and yet the model chooses a solution that uses only the target feature and ignores the spurious feature, and it performs quite well. Whereas here we see this doesn't happen. These are results from BERT. The trends are similar for other models. So here, when we find a case where the target is very difficult to extract relative to the spurious feature, it doesn't start learning till we've done quite a bit of data augmentation. And in general, the in-between values track in this pattern. So as this ratio gets higher, the models perform better with less evidence. And like I said, that was for BERT. That's also for T5 in the paper we have for other models, but they all look similarly. All right, so takeaway from there is basically that maybe it's not just this matter of features being there versus not there, but actually we need to look at the kind of quality of the feature representations at the starting point when we start training the model. And that's pretty intuitive. I think the more exciting thing here is thinking about, one, that we do have some ways of measuring this kind of how there the features are using things like this MDL metric. There's also this kind of implication about thinking in terms of inductive biases. So once we have pre-trained models that have features that are very readily available, then we can think of that model as having an inductive bias that forces it to use or encourages it to use that feature even in the absence of training data or training evidence. So ending just with a few points of discussion on that. I think the main takeaway is, like I just said, thinking about pre-training as a way of endowing models with inductive biases. So that really, that pre-training process really affects which solutions the model is going to prefer over other solutions. And when we're thinking about how to improve model behavior, like making them more robust or making them less biased, we have a lot of options, right? Like as ML builders of ML models, we can think about tweaking the training data, or we can think about tweaking the way that we pre-train. And we might not always have the same amount of control over both. So even if data augmentation seems quite appealing, there are often cases where we might not actually have control over what data we train on. I'm interested in this setting personally. I like to assume we don't get to choose our training data. And that's coming from kind of inspiration of human learning, right? Like you learn from a highly correlated world where you might not have the ability to solicit examples that explicitly decouple confusing features, and yet humans are pretty good. We come with a lot of inductive biases, and we're pretty good at learning generalizations despite having very skewed training data. So this kind of debate is pretty interesting in the kind of linguistics and cognitive science world and goes very far back. in terms of how much, quote, innate structure do humans have when we come into the world and start learning. And this has often been kind of pitched as an argument between neural network type learning and more feature-based, logic-based approaches. But I think that opinion has been shifting over the past couple of years, and this kind of results to me give kind of an encouraging way of thinking about pre-training as a way of getting that kind of innate structure, so we can pre-train models to prefer compositional solutions or more abstract structures, and then maybe we'll get better generalization behavior despite still training on that skewed data. Yeah, and I think finally, like we mentioned at the beginning, I've been increasingly interested in the kind of grounded language and robotics. So several of my current projects that I'm really excited about and would love to talk to other people about is whether we can get this, if we're thinking about learning good models of language, how much of this innate structure needs to come from non-language tasks. So a lot of the things that we need in language refer to, for example, notions of agents and patients taking actions in the environment, and the idea of objects persisting over time. Those kinds of semantic features play a big role in the meaning representations we want to build. So maybe we can learn that structure from tasks like vision and kind of embodied interaction. And then only later add in language and take advantage of all of that innate structure that might allow us to learn better generalizations, better groundings, and get out of this kind of text-only kind of chatbot setting that are language models, that are in this kind of uncanny chatbot setting. So that's a direction that I think is really exciting and promising. And that is all I have. So I am happy to take questions. I think we have plenty of time. Thank you.
Yeah, thanks, Ellie. I guess I will be the only one you can hear clapping. There are some questions in the QA section. QA, like the window here. One of the questions is from Sarah. Do the word pairs in probing sentence structure in contextual word representations, that paper come from pre-trained static word embeddings or the first layer of the contextual model?
Oh, good question. Probably don't need the slide, but might as well go back. Yeah, so we did it, I think, multiple ways. Since we were testing lots of different models, we defaulted to the first layer of the contextual model in each case. So in like the Elmo model, that first layer was gloves, so that was the same as the static embeddings. For BERT, they're like these word piece tokens that are a bit different, that are trained within BERT. So this is just showing the results for BERT. In the paper, we had results from several different models, and in each case, it was the first layer of the contextualized model. But we did know how static word embeddings performed because the first layer of Elmo is glove, which is static word embedding.
If you have other questions, just please put in the chat or put on the QA. So there's another question from Fan Bai. So he asked, BERT seems to perform well on linguistic probing tasks with or without fine-tuning on downstream tasks. However, the fine-tuning stage usually can impact the downstream task performance a lot. So does it mean the feature used for downstream tasks are orthogonal to linguistic features?
Yes, that's my interpretation. I think exactly. So when I see results like, like most of what I presented here, it's basically that it seems like you started with this really nice initialization where the model has these nice linguistic features, and then you're saying, okay, now you should do question answering, and it actually ignores a large number of those linguistic features. It obviously isn't ignoring everything you got from pre-training, because we see a significantly better results when we start from the pre-trained model than if we were to train from scratch. But the features that it's using are not the full set of features available to it, and instead it's what we tend to see, especially in things like squad and and natural language inference. So question answering and natural language inference is that the models are just using a lot of heuristics, right? And so they're learning a lot of task-specific heuristics. And that's what we see in like the lexical overlap example. And so that work that's happening during fine-tuning is that they're learning to use a lot of heuristics that lead to really good task performance. But they're not doing the thing that, I was hopeful they would be doing, which is figuring out how to use the great features they have available to them. And so I think part of my current understanding is the reason they're not doing that is that features are not available enough, right? So if we could make those features as salient, as available as those heuristics, then the model might actually end up using the good features. But if the heuristics are easier to extract and there's lots of them, right, then it's a little more work for the model to figure out that it should use the dependency parsing. So I think what we end up seeing is that the models they're solving downstream tasks in ways that are very driven by heuristics and make a lot of sense and lead to good performance, but don't take full advantage of the solutions they really should be able to learn based on what they have from pre-training.
Yeah, so here another new question from Sarah Vanguard. So probably give a little bit background. So Sarah is currently working with Mark Reader. So she actually with Yuval Pinter, who is also here. They wrote that paper like attention is not the explanation. Yeah. So okay, just give a little bit background who is asking this question.
I like that paper. Good to see you, Paul. Kind of see you.
Yeah, so Sarah is the one who asking the question. So Sarah asks, it seems that MDL controls for some possible confounders in early probing method, complexity of probe. Have you revisited your first hypothesis using MDL?
Yeah, actually. So like these types of results, whether the results would look different if we were to measure this in MDL rather than accuracy. And actually, I think in the supplementary, we did end up including those results, or maybe we footnoted it. So as we're working on this paper, that's when the MDL work came out, and we reran some of this using MDL, and we didn't see big difference. If I would have to double check the exact results. We didn't see big enough differences that we felt it warranted updating the main body of the paper. I think that was the main takeaway. But yeah, I'd actually have to double check. I'm pretty sure we didn't see it looked about the same. Like they weren't getting significantly less extractable. There were differences. There are huge differences if you look at the average over the embeddings versus just the last layer. And now I'm remembering, I think we initially ran MDL on just the last layer, and all of it like got way worse. And so we were kind of excited, and we're like, oh, that explains a lot. The features have become less extractable. But then, in fact, once you look at the average over all the layers, which is how we had done the accuracies, there's not a big loss. So we do see this consistently across all of the fine-tuning runs, is that the top layers do lose that linguistic information. So that suggests that those top layers are getting very specialized for the task they're fine-tuning on, which I think makes sense, and it also is consistent with the previous question was asking, right? That they're learning features that are fairly different than these linguistic features, and those top layers get overwritten to focus on these new features that are kind of task specific, and the linguistic information gets pushed back to earlier layers and is not really used.
Yeah. Any more questions from audience? Yeah, I have a high-level question, much more like given so many different architectures are proposed instead of transformers, so there's like different ways to layer them or like place the attention. So there's some research on that, and as well as there's so many different ways when people study to do the denoising or various ways they try to train this kind of deep language models. Do you think those would impact some of the conclusions you come from your work, or do you think your analysis largely will carry through with the variations of model architects or training objectives?
That's a good question. It's kind of hard to say. I mean, I think architectures do make a big difference. Like So I guess if the main conclusion, so I think that my main conclusion is, I think intuitive, I would imagine is true in many settings, which is just basically from the point of view of a fine-tuned model, you can either work with the features you currently have, which are right there, and you can learn weights over those, or you can work a little bit harder to pull out better features and then learn weights over those. And so if you have to work too hard, you're not going to bother doing it, even if it comes at a hit to accuracy, or you're going to find some other solutions. Obviously, the architecture affects how easy it is to find those features. So like in some other work we've been doing with some looking at like learning logical representations like and or, we see a really big difference between the type of signals that a transformer is able to readily extract and the type of signals that a LSTM is able to easily extract, right? Readily extract. So I think that the architecture would have a big effect on the behavior of the fine-tuning model, like the fine-tuning architecture, because that'll affect how easily it can access different types of features. And that goes very nicely into the inductive bias as well. So we think of like architecture as one of the main sources of inductive bias, like an LSTM has a nice inductive bias for caring about sequential order, whereas maybe a transformer does not have that bias. And so I would think of it as like the architecture and the pre-trained representation together kind of define the inductive bias of that model, as opposed to just one or the other. In terms of the architecture of the pre-trained model, I'm not sure. I imagine it does affect the representations, but I would be just completely speculating.
Yeah, let's see. I don't think there are any more questions. It's about time. Yeah. Thanks again for giving a very intriguing talk and super complete with a full line of research. And we're going to look forward to the new thing like you're talking about in the last slides.
Cool. Yeah, thank you so much. Good to see everyone, and thank you for the questions.